All right, everyone, here we go. The beginning of our last section of the year, 13.1, right triangle trigonometry, day one. So we're starting here with a picture of a simple right triangle. And I'm going to start by labeling these sides. For starters, the one that is a guarantee is the hypotenuse. And you might remember that from previous study of right triangles. We talk about it a lot with Pythagorean theorem. More to come on that later. We're going to bring that back today. And you can easily identify the hypotenuse because it is across from the right angle. Now, as for the other two, they're typically called the legs. And especially when it comes to Pythagorean theorem, we don't really differentiate between them. They are the two other sides. They're both connected to the right angle. They're the legs. But when it comes to right triangle trigonometry, what we do is we end up focusing on one of these other angles. Not the right angle, but one of these other ones. Now for this picture right now, I'm going to say we focus on this angle down here. That symbol I just drew is called theta. That's Theta, theta. It's another Greek alphabet symbol, and it's commonly used in trigonometry to represent an angle measure. So it's basically like a variable. It's an angle measure we don't know. We're calling it theta. Well, the rest of trigonometry now, right triangle trigonometry, is all based around the way the sides relate to theta, relate to that angle. So when I look at this side over here, as it relates to theta, it is across from theta. We call that the opposite side. Opposite meaning across from, it's across from theta. And then when I look at this bottom side, that is actually connected to theta, well then that is the adjacent side. Adjacent means next to, and this side is right next to theta. So that's called the adjacent side. The hypotenuse you don't have to worry about. The hypotenuse isn't in relation to theta. The hypotenuse is always in relation to the right angle. So find the right angle, find your hypotenuse, but then the other two sides get specific names based on how they relate to theta. Across from theta, not connected to it, that's your opposite, and actually connected to theta, that's your adjacent side. It's right next to it. Well, because of similar triangles, this basically represents all right triangles with a measurement of theta. Just pretend, for instance, that this was 40 degrees. Well, if this was 40, then I guarantee that's 50. Because 90 and 40 makes 130, that has to be 50. And if this was a 90, 40, 50 right triangle, then due to similar triangles, the sides are always proportional. So I can draw a really tiny triangle with a 90, 40, 50 angle measures. I could draw a really big triangle with 90, 40, 50 angle measures. And while this will have small sides and that one could have big sides, the proportions will always be the same, and that's due again to similar triangles. So because it's about these proportions, where trigonometry comes in then is making some ratios out of these sides. So the three trig functions we focus on today are the three classic ones, and that is sine, cosine, and tangent. You'll see sine is often abbreviated S-I-N. It's still pronounced sine though. And then you put the angle measure that you're doing next to it. For now, we're not using a specific measure. I just made up one if it was 40. We're going to leave it a variable. So it's the sine of theta. And what this defines is the sine of theta is a ratio that compares the opposite side to the hypotenuse. So from theta, here's the opposite side, here's the hypotenuse. We make a ratio comparing them. And again, that ratio would be the same for theta of any value. If it's sine of 40, then whatever numbers I put here, the ratio will be the same, as long as it's sine of 40. Now, if you do sine of 72, then it'll be different. But all those different triangles with a 72 degree angle, some big, some small, once you make the ratio, think like it could be a 2 to 1 ratio, well then it could be a 4 to 2. Or 8 to 4. It's always the same ratio. Moving on, cosine, abbreviated COS, still pronounced cosine of theta, is another ratio that compares the adjacent side to the hypotenuse. So that's the side that's next to theta compared to the hypotenuse. And finally, the trig function called tangent, that's abbreviated TAN, tangent of theta. That's the one that does not use the hypotenuse at all. It's the opposite over adjacent. Now, for our purposes right now, you don't actually have to memorize this, and you refer back to these notes whenever you're working on these problems. But if you would like to try to remember them, and if this was, regular school and we were in class, I'd probably be asking you to do so. There's a way that helps us remember the names of the trig functions and what they compare, and that's an acronym called SOHCAHTOA. And in short, that's reminding us that sine compares opposite over hypotenuse. Sine compares opposite over hypotenuse. There's the SOH, so. Cosine compares adjacent over hypotenuse. That's cosine compares adjacent over hypotenuse, CAH. And finally, tangent compares opposite over adjacent. Tangent compares opposite over adjacent, TOA. So SOHCAHTOA, a really easy way to remember the three classic trig functions and what they compare in their ratios. So after all that, let's go ahead and actually work on a problem. So we're going to evaluate the sine, cosine, and tangent of angle theta. Now you can see I've got a right triangle. You can see I've got a hypotenuse here labeled 13. It's across from the right angle. I've got one leg right here next to theta. We'll call that the adjacent side, and that's labeled 5. Now this opposite side is actually blank. So this gives us a little extra work at the beginning, and that's find the missing piece of a right triangle. So before I can do any of these trig functions, I'm going to first have to find that missing value. And to do that, I'm going to bring back, I mentioned it earlier, Pythagorean theorem, which, if you remember, is a squared plus b squared equals c squared. It's for finding the sides of a right triangle. And the one you lock in place, c is always the hypotenuse. You see it's on its own. C is across from the right angle. This is the hypotenuse. This is C. Now, as for A and B, they're interchangeable with Pythagorean theorem. Now, I know because of where I put theta, I know this is my adjacent side, and I know this is my opposite side. But as far as which one is A and which one is B, it doesn't matter. So you have to have adjacent over here because it's next to the theta. You have to have opposite right here because it's across from the theta. But as far as where I put the letters A and B, it doesn't really matter. So I'm going to put A over here by adjacent. I'm going to put B over there by opposite. And now I'm going to fill in the blanks. I have A is 5. That's 5 squared plus. I have B is a variable, so I'm going to leave it as B. 5 squared plus B squared equals, and then I have C is 13. C squared becomes 13 squared. So now I'm evaluating. 5 squared is 25. B squared, I'm going to leave it alone. 13 squared is 169. I'm now going to do a minus 25 on each side. So by doing minus 25, that cancels. Minus 25 over there is 144. And then I'm going to do a square root on both sides. And that leaves me with B equals, now the square root of 144 could be positive 12 or negative 12. Remember, square roots have positive or negative answers. But because this one represents the side of a triangle, I throw away the negative answer. I decide B is 12. So now I have all three of my sides of the triangle. So I'm ready to do my sine, cosine, and tangent ratios. So I come down here where I already have set up using SOHCAHTOA. Sine is opposite over hypotenuse. So when I actually plug in the numbers, then I'm going to say the sine of theta is, well, I find my theta symbol. I look for the opposite side. Across from it, that was 12. And then I look for the hypotenuse, and the hypotenuse is always across from the right angle. That was 13. The sine of this angle is 12/13. In the next one, then I can do the cosine of theta. Well, using SOHCAHTOA, that's CA, C-A-H. Cosine is adjacent over hypotenuse. So for cosine, I go back to theta, but now I look for the adjacent side. That was right here next to it. That was 5. Over, again, using the hypotenuse is always across from the right angle. That was 13. The cosine of theta is 5/13. And finally, for the tangent, that's tangent of theta, and that's SOHCAHTOA, that's TOA, T-O-A. Tangent is opposite over adjacent. So I go back to theta, I find the opposite side, which was 12. I put it over the adjacent side, which was 5. And that's it. Those are the 3 trig values for the sine, cosine, and tangent of theta based on this right triangle. So today you're working on page 856, numbers 3 through 5, but please only do sine, cosine, and tangent. They mention 6 trig functions. We've only done 3 of them so far. So when you work on problems 3, 4, and 5, you only do the sine, the cosine, and the tangent, just like I did here. And if you need to use Pythagorean theorem to find a missing side, refer back here to see how to do that. Thank you all very much.